Hello, everyone, and welcome to a new episode on Hyperbolic Orbits podcast. And today I'm really happy to have as our guest someone who's a brilliant space researcher as well as a true leader. We have with us today Dr. Andris Slavinskis, who is a co-founder of Nanocraft SIA in Latvia, working as a system architect of new mission simulation software Teleria for the development of autonomous rendezvous, proximity operations, docking, and robotics operations. As a professor, Dr. Slavinskis is supervising PhD students at Riga Technical University in Latvia on photorealistic and trajectory modeling for the ESA Comet Interceptor mission, and at University of Tartu Observatory, leading the MSCA doctoral network e-sailors. Thanks a lot, Dr. Andres, for joining us today.
Yeah, thank you, Sumana, for inviting on this interesting topic to talk about, space and my work. Yeah, we're excited to have this podcast.
Thanks. So let's begin. Let's start from where you started studying and how you reached this point.
Yeah, okay, that's a very good question, and I typically like to answer this question because I think it has a lot of meaning in my personal development, how things went on in the space career. So I started with bachelor's and master's in computer science, and at the time I was not doing any space. So I was working on kind of software problems. Did my bachelor and master thesis related to making software for scientific applications, and that I really enjoyed. And then after finishing my master's, I was thinking, well, doing a PhD sounds like an interesting thing to do. Maybe I had nothing better in my mind, but then I was looking at the opportunities around me, like people I know applying to places where people didn't know me. As typically it happens, a personal contact helps, and so I got a PhD position at the University of Tartu, and that was a huge change in my career because I joined the ESTCube-1 team. It was the Estonians, like a tiny country neighboring Latvia. They were building their first satellite, and I had a chance to be fully integrated in that team because I was doing PhD full time. And although it was a new topic for me, still in the space technology sector, we can have a lot of computer science, because satellites are computers, they are robots, they are autonomous, and before we launch them to space, we have to do a lot of simulations. So this is what I did in ESTCube-1. I used my computer science background to simulate some of the most interesting problems, at least in my opinion, some of the most interesting problems that we had in ESTCube-1. I was simulating attitude determination, I was simulating attitude control. We had to do fast spinning, which was rather unusual, which is rather unusual for space systems. But yeah, that was my PhD. I don't know if I should go on with the other steps, or do you have the next question in mind?
That's a great introduction. And that actually brings me to my next question, is the ESTCube mission. And that's how I know that you are a very good space researcher and a leader. So could you tell us more about the mission and whatever happened around that? Technically, it was a team, it was a student team that evolved into doing something really good. So if you could elaborate more.
Yeah, sure. Okay, so as you said, it still is a student, like ESTCube, or what is coming after it. It's called the Student Satellite Organization in Estonia now. But what we did and are doing with ESTCube, it's always like this. We can take opportunities that maybe are too risky for others to take. There's maybe no business at the time, or the scientific or technical challenges are way too difficult. And with ESTCube-1, and then with ESTCube-2, and also with ESTCube-LuNa, which I will talk about specifically later, uh, we took a challenge to demonstrate the electric solar wind sail. And for me, when I was finishing my, after finishing my master's and learning about this technology, I got very excited that someone in the world recently, so that's already, for me, it's like 15 years ago, and then recently meant that in 2004, someone invented a new propulsion system. And to me, that was, mind-boggling that, well, is this still like, there's still room for inventions there? That's amazing. And then the opportunity to directly work with the people that invented it, Pekka Janhunen and colleagues, and to develop a mission that would test it, that uh, provided me with has provided me with excitement for many years. And you'll see, it kind of hasn't stopped. I have moved to other directions as well, but overall, electric solar wind sail is a big passion of mine. And so the reason why we were able to take, why a student project like ESTCube is able to take more risks is the following: that uh, the goal, one of the primary goals of the project is to educate. And you can educate people doing simple things, but you can also educate them by challenging them to do very complicated things. And testing the electric solar wind sail, I think in my life it's the biggest challenge thus far. Maybe like I'm also involved in ESA mission Comet Interceptor, which is bigger, which is somehow more complex and so on, but it has an ESA backing. It has this decades of experience behind it. But with ESTCube and with eSail, we're kind of starting from scratch, like how to build it, how to simulate it, like all these tools, the basic tools to analyze an eSail type of mission, we have to build from scratch. And well, for students, I would say that over these almost 15 years I've been involved with ESTCube, I have seen that it is maybe one of the best ways to educate people, like this kind of hands-on project. I mean, maybe it sounds weird from me as a professor to say that lectures are not good for education. I'm not a big fan of giving lectures, and maybe this kind of podcast is even better for education. But hands-on project is the best because you give students the ownership and responsibility to actually make the project happen. And no single professor or senior engineer can do all of those things. It's just too big and complex. So giving the actual, mission or space engineering tasks to students, I think has been proven very successful. And in Estonia, now it's of course the space sector has grown, but there was a time when most people that worked in space sector in Estonia were coming out of ESTCube, and that was I think great success for the space sector to grow even further as it has done, and now it's much more diverse. Yeah, it's amazing.
And I remember there's this big photograph of the ESTCube team, some of the members who went to mission control when the launch happened at the observatory. So, how was it when you launched the first satellite, when you launched something to space for the first time?
Yeah, well, one thing, first thing that came to my mind, we were very tired because it happened in the middle of night, and we had to wake up at, I don't know, 3 or something. There's almost like no point to go to sleep. But apart from that, I mean, I guess everyone was very anxious because student built satellite, the first one of the country, led by people that have not led. Now I can say this freely because so much time has passed, that people that had not led space missions before. I mean, there are a lot of things that could have gone wrong, and but it worked. So we were very lucky. I say that basically, so a few hours after the launch, we got the signal and we were able to operate the satellite. There's still a lot of work ahead of the team to update the software, to troubleshoot, and so on. But we have seen later on that so many things can go wrong with communication system, with the launch system or something. And with SQ1, we were very, very lucky, yes, that it was operational and all the like subsystems worked. And then came, about 2 years of operations, and well, kind of this excitement and anxiety went on and on, because over time we attempted to do the electric sail experiment, and unfortunately that didn't work out for us. But at the same time, it gave us a lot of learning experience on how to troubleshoot a satellite in orbit, how to look for problems, and how to see that, we see something in data we don't understand, and then some very smart people were thinking what is happening there.
And from that to now, I want to fast forward a bit to Comet Interceptor. It
Yeah.
sounds like a fascinating, like the case study of a fascinating deep space mission. So if you could tell us what the mission is about and what your role specifically is in that.
Okay. Yeah. Sure. Comet Interceptor is thus far very unique and ambitious mission, whose goal is to fly by an Oort Cloud object, or we also call it topic Oort Cloud, because Andris Topic, an Estonian scientist, have also played a role in in putting out hypotheses that this Oort Cloud exists. And of course, nowadays, mostly we know it as the Oort Cloud, something that is thousands of astronomical units away from the sun. And these objects there, we're not observing them directly, but we know that the comets we have near the, you know, they're called short period comets. So the ones that are near the sun, they come from the Oort cloud, and we know it because we see that new comets are coming from somewhere, and we can calculate from the orbit where they're coming from, more or less. And then some of them remain, orbiting the sun. But then when they orbit the sun is heating them up, and they are losing mass. And this is, you see it in tail. There are jets. There is atmosphere or coma. So all this is an activity of the comet that kind of defines what the comets are. And if they go on like this for a few million years, they would actually evaporate, disappear. But the solar system is 4.5 billion years old. So there's a reservoir of comets. And that's what we call the Oort cloud. And then some of my partners in the Comet Interceptor mission, already in 2018, if I remember correctly, they proposed an idea that we could have a spacecraft flying by one of these objects. And this is very, very challenging, because we don't know which object, we don't know how it looks, we don't know where exactly it's going to come. So this is the first time we are building, and we, the whole world, we're building a mission to an unknown target. Okay, and there are lots of challenges there. So, for example, we have to develop our instruments without knowing exactly how this target's going to look. And so the way that the target is going to be chosen is the following: that there's a dedicated observation team or target selection team that are using some of the most powerful telescopes we have nowadays, like Vera Rubin Observatory and James Webb Space Telescope. And these telescopes, they're so big and powerful that they are finding Oort cloud objects more often than we used to do. So the Comet Interceptor mission was developed with these new observational capabilities in mind. And we see that it's already happening, that more and more new comets are being found. That's great news for us. And then we will be, or this target selection team will be looking at particularly at comets that come So at the ray in the near proximity of the Lagrange point L2, that's where the Comet Interceptor will be parked, and it's going to wait for maximum 2 years for a suitable target to be found. Okay, and this is very, 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 very difficult already. And then when the target's found, then the Comet Interceptor mission will make a maneuver towards that target. And before we fly by this target, we would like to know as much as possible about what we expect to see. So typically, let's say in case of a Rosetta mission, the target did change because there was a launch failure. They had to postpone launch failure of the rocket. And they had to postpone Rosetta launch and change the target, and that was already a big headache. So now we're looking at the kind of mission where we're going to launch it, and only then we're going to find the target. And so when this is happening, then we would like to, with remote observations, get as much information as possible about the target and put it inside our models. And so that instruments would be able to update their parameter spaces on what is expected to be measured, okay? And our contribution there, well, back in the day, 2019 to 2021 or something, I was part of the instrument called Optical Periscopic Imager for Comets, and together with Mikkel Pajusalu, who is still leading it, and we were establishing the first Estonian space science instrument, writing a lot of documentation, and at some point maybe it became a bit boring, so I left. But already, back then I knew, and it was coming from Mikkel Pajusalu, that we can also do much more fun stuff, like model comets in Blender. So in order to understand what the cameras will see, we want to make photorealistic models of the comets and of representing what the camera would see. And so we're now running a project in Latvia, or this is already a project extension, which is going to end in a month or two, where my engineers, and they're also my students, they are making models of comets, like the nucleus of the comet, of the atmosphere of the comet, of the jet and tails, and also of background stars. And then also Comet Interceptor has something like 7 cameras, and depends how you count. And each of these cameras work in a different frequency range. They have different fields of view. They have different viewing geometries and so on. So we are using Blender to represent this kind of different aspects of how the Comet Interceptor will work. And hopefully with the next project, we're able to put all the cameras together and simulate this flyby and output all the the visual feed that the cameras would provide. Currently, we have worked with 3 instruments, but this is now being extended to hopefully include all cameras.
Oh my God. So if I understand it, you're launching it 2029, is it? Launch
I
date?
think so, yes. You know how it's space project. But I think
Yeah.
that's the
And
plan, yes.
then you launch it and it goes to an L2 point, and
Mhm.
then it waits, and then it observes, and then you,
When we observe from the ground and from
yeah.
like space telescopes. So the Comet Interceptor itself it's not a telescope. The cameras it includes are maximum this big. But Vera Rubin Observatory, huge telescope.
And then the target, it spots the target, and then it starts telling its payloads, okay, this is what we are going to measure. Oh my God.
Yeah,
Okay,
so
I'm just,
basically we will get some data about the target. Then we can start to model it and see what the cameras would see, how bright it is, how fast it is, and so on. And then we can send to the spacecraft, like, let's say, camera parameters. What is the exposure time? How often the images should be taken? And what is the maybe dynamic range and things like that. So that will be, so we cannot update software per se. It's not for developing software because that should be finalized soon, but it's about the camera parameters that the instrument can update. Yes.
Well, I wish both you and Mikkel all the best. It's a very strong team, and this is a really fantastic mission that we are all looking forward to.
Yeah.
Now,
Thank you.
Andres,
Thank you.
of course, and you are a professor, and before that, also, you have led teams where you have literally taught people how to do things. So, we are going to introduce a micro lecture segment in this podcast where every guest has to choose their favorite space topic and teach us. So, what are you going to choose, and what are you going to teach us today?
Yeah. Okay. Thanks for this opportunity. Really excited about talking about electric sail, and for well multiple reasons. Because I spent in the recent past, I spent a couple of years making a concept called ESTCube-LuNa, and I will discuss this in detail. But before we dive into that detail, I would actually like to share a video with music made by my friends, musicians here in Latvia, and have a little break from talking, and then I will go to slide deck and then show all the technical details. But all right, so this is how we imagine the ESTCube-LuNa mission to work, and it also has been very exciting to be producing such videos and working with artists. But now I'll talk about a bit of technical details about this mission and why we are building it. Okay, so the story about propulsion, and the story about propulsion is about there's technologies that we are using already, and then there are technologies that are emerging. And so for most missions that have been flying in space and in deep space, those have been equipped with chemical propulsion and electric propulsion. So here on the top left, you can see Cassini spacecraft by NASA, which is using chemical propulsion, and basically you can think of it as like as a robot built around its propulsion tank. The propulsion tank takes most of the space in this mission, which went to Saturn. And then with electric propulsion, we can be a bit smarter. So electric propulsion is more efficient. It has so-called higher specific impulse. So each particle that is being thrown out of the satellite has higher speed. So it is giving more to the change of velocity or delta V to the spacecraft. And there the propulsion tank can be smaller. And this is a Rosetta mission by the European Space Agency. However, we need to charge. So electric propulsion means that we need to charge these gases that are in the tank, like xenon or argon, and then we have huge solar panels, and we couldn't fit them on this one small window. But if you check around for the Rosetta mission, it has massive solar panels. Then the next one we have, and think that this is think that chemical propulsion is expanding in 3 dimensions. Electric propulsion is kind of in 3 dimensions, and the wings are in 2 dimensions. And then we have the light sail. This is a JAXA spacecraft Icarus, which was actually flying in deep space and tested the light sail. And the light sail is a reflective surface which is expanding in 2 dimensions, and it has been tested already. And then we have this newcomer, the electric solar wind sail, or simple e-sail, which is a wire or tether which we can deploy in like 1 dimension. There can be multiple of these tethers, no problem. But think that if we build one, we can build multiple, and each one of these is like a 1-dimensional thing to deploy. We still haven't managed to do it, and there are some missions in works to do it in a low Earth orbit. The next one that will be launched very soon is 4SAIL-1P, built by Finland, by Aalto University, by Finnish Meteorological Institute. And most of the rest of this talk will be about what we want to do beyond low Earth orbit in lunar orbit, where we have the solar wind, as opposed to when we do tests in low Earth orbit, then we are making them in the ionosphere, which is similar, like plasma environment, space plasma environment, but not really the same as the solar wind. Okay, for many of you who know propulsion systems, this is going to be very simple, but maybe some of you who don't, then this might be valuable to know that in order to change the orbit with chemical propulsion, let's say from this closer to the sun to the one further away from the sun, we perform so-called impulsive burns. So chemical propulsion has a high thrust. It has low specific impulse, so it's not very efficient as compared with electric propulsion, but it has high thrust. So it gives a kick, and we can go to this highly elliptical orbit, and then we make another kick here, and it goes to circular orbit. But then with low thrust propulsion systems, which are electric propulsion, which are not chemical, of course, but the light sail and the electric sail, we go into these orbital spirals. So slowly but steadily, we can go from one orbit to another. That's a bit of theoretical background. And then some, well, maybe I won't spend too much time on this. So, but just wanted to show it, you can pause the video here and read these details. But just to give the main idea that solar wind was discovered. Then on top of that discovery, inventions were made like magnetic sail and electric sail. And electric sail is something we've been developing in many missions. This is slightly outdated, but the main principle is the same, that we can do tests in the low Earth orbit ionosphere, but then actually our real environment for the electric solar wind sail is the solar wind. And in the Earth orbit, in low Earth orbit, we are protected by the solar wind thanks to the Earth geomagnetic field. And this is good for us because living in a constant solar wind environment would not be healthy for us. And luckily, we see it only as auroras. And sometimes, when it's very strong, then it kills our satellites. So I don't even want to think what it would do to us if we would be directly affected by solar wind. So for better or worse, we have to go to the solar wind somewhere far away from the Earth, such as lunar orbit. And that's for lunar orbit, we have proposed this ESTCube-LuNa concept. And then if we test that, we have many other opportunities. We can talk in some other podcast. And then another thing I want to mention is that we are in this business of CubeSats. So I don't have funding to build like Rosetta. Like this is how big Rosetta is, by the way. I don't have funding to build a Rosetta type of mission. So here are considerations what are different between CubeSats when we do them in low Earth orbit, what are the and how it compares with the spacecraft in deep space. And then when we are making deep space CubeSats, or we also call them nanospacecraft, then we have to kind of rethink our communications, our autonomy solutions, our navigation solutions, and attitude determination solutions, and propulsion solutions, which are all different than if you do them in low Earth orbit and if you do them with big spacecraft. Again, feel free to pause here to read this. I'm not going to go too much into detail because I would like to discuss this fairly recent publication. I guess it went out last year, yeah. So this is our concept for ESTCube-LuNa, or electric sail test cube lunar nano spacecraft. And I was so remember I said I was very motivated to work with the people that invented the electric sail. So here, not only that, we had a chance to have a special issue on advances in CubeSat sails and tethers. And this was done together with the e-cell inventor, Pekka Janonen. So I felt that, 1.5 years ago, I had this one of the peaks in career where as a professor, I delivered a special issue. And more so, I did it with my friend and, source of inspiration that has invented the e-cell. So it was a big thing for me. But, we have to move on and try to figure out how to build it. And by no means it's a simple mission. So now we go into detail what this electric solar wind sail is. So we have charged particles coming from the sun, and we use solar wind protons for in the case of e-sail, and then they are coming and meeting or encountering the spacecraft. And how we run this electric sail is in the following way: that the spacecraft. So first of all, the spacecraft is spinning up, as you saw in the video, and then it is deploying this wire, or we call it tether. And it can, so in our experiment here, it can be about 1 kilometer long. So this is a big structure, but the tether it's a hair thin. It has this redundant structure, like a chicken wire a bit, but all these wires are very, very thin, so it doesn't weigh much, and that's very good because it would be a problem if it would be heavy. And so we deploy it, and the whole thing continues to spin. And this spin is required to actually keep the tether stretched. And then this whole spin plane, we think that this whole spin plane is used as a sail, where we can control different aspects like the orientation of the sail and where it's charged and so on. So there's less control in this ESTCube-LuNa concept, but still also a big operational electric sail would be spinning, and it has there are several papers that describe how to control it in this kind of spin manner. And that's what I said earlier, is that we have to reinvent all the aspects of this propulsion system, how it's operated and how we analyze the missions, because even the geometry, how it works, is different, and it's not included in normal mission design tools. So, but here we have a simple version where we have a CubeSat and it has a fixed spin plane. We don't try to change it, but we wait for the right moment when the spin plane is directly encountering the solar wind, and that's when the maximum E cell thrust is generated. And we have to bias the whole thing, so the electric cell is charged positively. So we have to bias the whole system, and therefore we have electron emitters that are. This is not like a thruster. This is, we show that we get rid of the electrons in the system. And so, as I said, the spin plane remains fixed inertially in space, and we generate thrust when the spin plane is facing the solar wind. But we can also generate torque when the spin plane is aligned with the direction of the solar wind. This is a maybe rather complicated graph, but the idea is such that, you know, solar wind comes from right to left, and then this whole thing is spinning. And imagine that if we charge it in this upper part, we're increasing the spin rate. And actually, this increase in the spin plane spin rate is something we can measure much faster and easier than the thrust. But however, thrust is the main thing we want to measure. This would indirectly tell us that yes, there is torque, which you can, you know, translate, use physics to translate to some thrust value, but it's not ideal case. But anyway, so this will happen at some point in orbit, and then 3 months later, this will happen. So over the year, we get these 4 very good opportunities to measure the E cell thrust and torque. And then in between, we have non-ideal conditions where we analyze this case. Now, moving on, what exactly would happen in orbit? So now we see so here's the ESTCube-LuNa orbit, and we see it from the top. And the sun direction is here, this yellow line. And now I said that the spin plane will be facing the sun. We will wait for that moment in time when it's happening. And then we can either charge it when being in this red part of the orbit, or in this green part of the orbit, or in the red part of the orbit. I think that when we are in the green part of the orbit, we are going away from the sun, and the solar wind is kind of pushing us. So in this case, our orbital altitude would increase, and then on the other side, we would when we charge the sail on this side, then our orbital altitude would decrease, so get lower. And this second case where the altitude and orbital period is decreasing is simulated here, where we compare a satellite. So this is used. I use GMAT in this simulation, and we just say that it is electric thruster with similar performance as we would expect from the electric sail, but the thruster is not changing the satellite mass. So this is idealistic case. You can simulate in GMAT, and then this blue line represents the satellite if it would stay in the same orbit as initially. And then there's the second satellite that is starting to perform like thrusting here and reducing the orbital period and reducing the orbital altitude. And this is the difference we would effectively would like to measure. And then we also have like cameras for monitoring the satellite or the tether. And for, of course, we would never see such a view. It's idealistic one. And we also have these cameras, as you'll see later, for navigation purposes. Okay, another rather complicated slide, but I'll try to give the most important details here. Okay, so the satellite is in lunar orbit, and we have to do several things with it, apart from in order to run the experiment. we have to communicate, and we have to navigate as a minimum. And for communications, for day-to-day communications, we plan to use like these simple antennas that you can, so these Yagi-Uda antennas, and communicate with an antenna in Tartu Observatory in Estonia. But in order to get scientific data down, and in order to perform ranging, then we would like to communicate, use the radio telescopes in Irbene in Latvia, operated by Ventspils International Radio Astronomy Center. So these are big dishes. Like there's one 16-meter one, and there's one 32-meter one that are repurposed for two-way communications. And this is what we would like to do for ranging and for getting more data down. We're not talking about a lot of data, but still, we need some better solution than this Yagi-Uda. On top of that, we have navigation cameras here, and also here. And these would be imaging objects around us. And we would like to develop a triangulation method for determining position of the satellite, and put it together with some simple orbital propagator that is running on board in order for the satellite to know its position. So these are some ideas for the concept of operations. These are some of the technologies that we have considered, like antennas, and antennas on the satellite, antennas on the ground. Antennas on the satellite, these are just examples, but about ground antennas, this has been a pretty strong push towards there. And also Ventspils University of Applied Sciences is our partner in one of the projects I'll mention in a sec. Then, in order to control the spin rate and to deploy the tether, we have this setup where we have thrusters placed opposite side from the tether, and 4 of them are used to control the spin rate, and then four the red ones, so going back and forth, and then the green ones are kind of to control the orientation of the spin plane. But this is more before we start to deploy the tether, because as soon as there's enough tether out, there's huge angular momentum in the system, which we cannot that easily overcome with these thrusters. But before we deploy it, we'll be able to spin and turn the spin plane. And a bit zooming into the attitude solution. So these are tiny thrusters developed by Technical University of Dresden in Germany, and these are tiny cameras developed by a company called Crystal Space in Estonia. And here are the thrusters. Like they look like too small, but they have actually been tested in orbit. They're called nanofeed technology, and they use a metal as propellant. In this case, it is gallium. Maybe something else will be developed for ESTCube-LuNa. We don't know yet, but Technical University of Dresden knows how to do these things. So this is the consortium that have been helping me to make this concept a reality. And then I would like to add that we have got a project which is under the Marie Curie Actions Program, funded by EU, the project is called Electric Solar Wind Cell Doctors, or e-sailors. And we will have an opportunity to hire 15 PhD students across these universities that you see here. Some universities have 2 or 3 positions, and these students will work pretty much on all aspects that I showed right in my last slides about the novelties of the ESTCube-LuNa mission and concept. And this is going to be kind of the brain power for this mission. And we still have to fundraise for hardware. We have one proposal for ERC synergy rejected, we'll certainly resubmit it. But yeah, this is our list of partners, and this is the end of the slides. Hope I didn't go too much over time. Uh, Thanks for listening to me.
Thanks a lot, Andris. This is so beautiful. The mission, the presentation, the visualization. I have one question though. This is so complex in terms of design. And when after the launch, you also have to operate this. This is operationally complex too. So,
Yes.
at what point do you start working with the operations team, saying that okay, this is how we are going to manage it, and this is how we are going to change things?
Yeah, so it's pretty much from the day one. Well, of course, we made like ideas about the experiments and some technical solutions first, but it's been several years since I'm in touch with the Ventspils University of Applied Sciences, where they operate these uh, dishes on the ground. And actually, this is where I did my bachelor's and master's. A lot of the partners you saw on the last slide, I've been somehow involved with them working there or so on. So anyway, Aalto University was missing there. They joined the e-sellers project, but initially in the concept, I did not include them because well, they're busy making this 4-cell 1P mission, which I mentioned before. But anyway, going back to operations that you asked about, is two of the students that I mentioned, the e-seller students, they will be working with communications and with making plans for operations. And there might be also a collaboration with another network that is where these radio telescopes are also included. So it's work in progress how to plan and do this. And I think for a mission where there's a lot of novelty, one should think about operations as soon as possible. Yeah.
Right. And you have been talking about nano spacecrafts, not just when we think of nano satellites, we think of CubeSats, but CubeSats in the sense of Earth observation mainly. Most people think like that. But I've heard you speak about nano spacecrafts going for deep space exploration.
Yeah.
So, how do you see that field progressing now?
Well, yeah, that's a very good question. So first of all, nano satellites, nano spacecraft. That's where it comes from, and I don't know how nano satellites is how common the term is nowadays, but CubeSats and nano spacecraft almost the same thing in my mind, and also with nano spacecraft, we want to nano spacecraft in my mind. It's almost the same thing as deep space cubes. We want to put emphasis on that fact that they are operating differently in terms that they are outside the Earth's magnetosphere. So the magnetometers and these magnetic actuators cannot be used for changing the for measuring and changing the attitude. So we have to use these thrusters when we go to lunar orbit, when we go to deep space, and that's often not often CubeSats have thrusters, and this is a fairly new technology, very exciting to work with. What else we have to do differently is that maybe we have to, most likely we need to have a star tracker in deep space, and we have to think of maybe we need to have a propulsion solution not only for attitude control but for different purposes. And so the field is certainly progressing very well. There are a lot of ambitions, and for example, already it's a like some years ago. I don't remember how many, but so Marco missions were assisting Mars mission and transmitting data and so on. And now there's for example, Milani CubeSat on the Hera mission on a way to an asteroid. So there are cases where these CubeSats are used in space agency missions. and that means that they are fairly mature. But having said that, they will never, like, we think sometimes, maybe when we talk about CubeSat missions, we think something in the range of hundreds of thousands of dollars. Maybe that is still possible, maybe, well, not in my experience, but maybe someone can do it. So, but when we talk about deep space missions and we want to provide high reliability, and there's a lot of this new advanced technology on board, we talk about millions and tens of millions. So they're not anymore that cheap, and it's not like students can just pull it off without funding, as sometimes we have tried to do. And yeah, that's the difference, is that someone like at a very high professional level has to take responsibility to carry out these missions. And certainly there are way more than I mentioned, just that mentioning something, the first ones that came to my mind.
Right. And my last question would be, although I do want to keep asking you, but keeping track of the time, my question is, you've been connected to student teams since your student days. And what
Yeah,
would be your advice to teams who are building satellite missions now when they are at universities?
yeah. I was thinking about this question maybe more than about other questions, because it's a hard one. Um and my answer is that as a student working on a student satellite project, you have your supervisor, or you yourself, you have to figure out a way to motivate yourself with some kind of intermediate goals. So if you're entering a university degree for 3 or 5 years, you might never see that satellite being launched during your university years. So you have to be happy about contributing, but not necessarily seeing the project going through all the stages. And what is even more important is that, and this has happened to us with SQ2, something might happen. Launches are difficult, satellites are difficult, so your mission might never work. And it's better to be mentally prepared for the situation that something does not work out as you expected. And to me personally, when, well, I was looking back now, maybe I was naively hoping that SQ1 ESAL experiment will work, and that would be a huge achievement of the mission, and so on. But it didn't. And now looking back, I'm thinking, well, maybe my mental health was not in the best place, living with those expectations and actually not getting results. And it maybe took a couple of years afterwards, the mission was over, for me to get over that complication. And so I would say that these missions require, or student satellites require, as much engineering skills as like mental ability to handle unexpected scenarios. And of course, supervisors play a big role there, but at the end of the day, each of us are with our own mental states, where we want to sleep and where we want to be happy and so on, and we have to be prepared for um unfavorable scenarios. And maybe to add on a bit, to end on a bit better note, is that you are in the uni and you are in the student project to get educated, and that should be your number one priority, so you are a better professional. And these projects can so specifically student projects can fail. They are maybe there to for us to learn from failures. Because if you
That's yeah.
just to add that, if you would do
Mhm.
it like space agency style, then you would write documents for half of the time or even more, and that's coming with its own mental problems. So maybe do a lot of engineering and fail is better than do like super high reliability, but then the project lasts for decades.
Yeah, that's great advice and good tip on the documentation, which sometimes students don't anticipate when they start working on a mission. But Andres, I want to thank you. This has been a wonderful episode, right from the beginning to the end. You've taught us so much. Thanks a lot for being with us. Thank you.
Yeah, yeah. Thank you. Yeah, great questions, and I really enjoyed talking here.
Thanks. And I hope everyone who is watching or listening, I want to tell you that Andres has been inspiring people for over 10 years now. And he has done the same on this episode. And I promise to bring more such guests. So stay subscribed to this, follow this podcast on Spotify, and share with your friends. And let us know what kind of new space things you're getting to learn from this podcast. It would really help us. Thank you, Andres. And I'll see everyone else in the next episode.